help of experts from various institutes, colleges, universities. So the idea is to encourage discussion, interaction, and learning new things as far as possible. And we are also conducting these talks in the local language Kannada also, with the intention of encouraging the use of Kannada in higher education. Now, every education is right from even Raman goes on saying that we have to introduce local languages at all levels, higher education. Only then our students will be comfortable, they can learn properly, and it becomes more effective. But due to various reasons, which we all know, we may not, some of them we may not know, our government, our education system has not been able to introduce these local languages at higher education, unfortunately. So that would be the ultimate, what we might call self-dependent, Atmanirbharta. Not only the materials, but even when we develop everything on our own, the languages and the lab, everything, I mean, science in our own languages, then we can say really we are self-dependent. And this is the case with even small countries in Europe. I don't know why we have not been able to do that. Every small country in Europe or the developed country, say Korea, they conduct higher education. Japan in their own language. They don't worry about English, French, and German. So of course they take knowledge from those languages and convert them. Anyway, this is also one of our objectives, to introduce local language as far as possible. And today's speaker is definitely well versed in Kannada, so you can interact with him in Kannada for a change, and also give your comments so that we start giving up our inhibitions of not using Kannada in higher education. ಒಂಥರ ನಮ್ಮನ್ನು ನಾವೇ ಕಟ್ಟಾಕೊಂಡ್ಬಿಟ್ಟಿದ್ದೀವಿ. So anyway, we have to get out of that somehow. It may happen slowly. Okay. So before I request him to speak, before I request him to speak, I will introduce the speaker briefly. Even though you may be knowing very well who the speaker is. Professor Rudraswamy, as you know, did his BSc, MSc, and PhD from Mysore University. He is one person who has done teaching at so many levels. He has taught at Government Polytechnic in Kerala, Engineering College in Chikmagalur, Pre-University College in Chenpatna, Government First Grade College in Chenpatna, Government First Grade College in Mandya, before joining the university in the year 2000 as senior lecturer. Since then, he has gone up the ladder and become the reader, associate professor, and professor, and retired in the year 2018. He has a total teaching experience of 34 years and total research experience of 26 years. He has published research papers numbering over 129. And he has guided 10 PhD students to their degrees and 3 MPhil students during his career. And he has attended several international conferences and delivered talks there. Just to name a few, he has attended the 10th International Symposium on Radiation Physics in Portugal, 20th International Conference on the Applications of Accelerators Research at Fort Worth, Texas, 11th International Symposium on Radiation Physics in Australia, an International Conference on Structural Compounds in UK, and so on. He has visited several countries like Portugal, France, USA, Thailand, UK, Spain, Switzerland, Malaysia, and so on. And he has been awarded the Nucleonics Best Paper Award for the presentation of a research paper entitled Bremsstrahlung Dose of Therapeutic Beta Nuclides in Bone and Muscle in 2012. He has completed several research projects like the research project on nanoferrite materials, synthesis and characterization for low and high frequency applications. The DAE BRNS major project on compilation of experimental nuclear reaction data using XFOR editor. And he has been a life member of Indian Society for Technical Education, life member of Indian Society for Radiation Physics, and member of International Society for Radiation Physics, and so on. He has been a coordinator of several workshops and conferences, and has served as a guest faculty at several institutions. And finally, he has delivered invited talks at several conferences and so on. So with this brief introduction, I will request now Professor Rudraswamy to talk about nuclear reactors for about 50 minutes and answer questions afterwards. Thank you. Now over to Professor Rudraswamy. Now you can.
Thank you very much, sir. Karnataka Physics Association ಸನ್ಮಾನ್ಯ ಅಧ್ಯಕ್ಷರಾದ ಪ್ರೊಫೆಸರ್ ಬಸವರಾಜ್ ಕಾಗಲಿ ಅವರಿಗೆ, ಸನ್ಮಾನ್ಯ ಕಾರ್ಯದರ್ಶಿಗಳಾದ ಪ್ರೊಫೆಸರ್ ಪಿ ನಾಗರಾಜರವರಿಗೆ, ಎಲ್ಲ ಪದಾಧಿಕಾರಿಗಳಿಗೆ, ಎಲ್ಲ ವೀಕ್ಷಕ ಸ್ನೇಹಿತರಿಗೆ ಈ ಒಂದು ಸದಾವಕಾಶಕ್ಕಾಗಿ ಉತ್ಪೂರ್ವಕ ವಂದನೆಗಳನ್ನು ಸಮರ್ಪಿಸುತ್ತೇನೆ. ಸೊ ಇವಾಗ ಐ ನೌ ಸ್ಟಾರ್ಟ್ ಮೈ ಟಾಕ್. ಸೊ ಐ ವಿಲ್ ಸ್ಪೀಕ್ ಆನ್ ನ್ಯೂಕ್ಲಿಯರ್ ರಿಯಾಕ್ಟರ್. ಇಟ್ ಈಸ್ mainly on general information, of course, so everyone can easily follow. So when you begin with nuclear reactor, so you have to first concentrate on nuclear fuels. It is the primary thing is required. So natural nuclear fuels are uranium and thorium. So this is how the raw ore and monazite minerals look like. Uranium raw ore, thorium minerals, this is how it looks. And of course, natural uranium isotopes are there. One is uranium-235 and uranium-238. 235 actually stands for mass number. Of course, 238, of course, this is another mass number. See, of course, the uranium atomic number is 92. Both have 92. And when we are talking of nucleus, we always concentrate on mass. Mass number is important. That's why I use that mass number here. So these are the two isotopes present in the natural uranium. So of course, in uranium-235 and 238, if you take, so you can use the uranium-235 as a fissile material. What do you mean by fissile material? See, in fact, it undergoes fission. It is important for nuclear reactors. See, material should undergo fission. And what is the fertile material? It is not a fission material. It doesn't undergo fission. So in fact, you have U238 is fertile material. Both are together in the natural uranium. Of course, you can always convert this fertile material into plutonium-239, which is a fissile material. Okay, so next stage, you can convert fertile uranium-238 into plutonium-239. So as far as natural uranium is concerned, these are the two isotopes you can think of. Natural thorium, of course, there is no isotope. It is 100%. It is the thorium only. So of course, but the thing is here, its mass number is 232. Okay, and of course, atomic number is 90. So it is a fertile material. It is not a fissile material, but it can be converted into 233 fissile material. So there is a okay. Of course, you can understand later on how to convert fertile into fissile. Later on, you can understand. So next. So see, this is uranium-238 and 235. In this table, you can see the abundance. In fact, in natural uranium, the abundance of 238 is 99.2745. Most abundant material in natural uranium is 238. 235 abundance is very less, the 0.72, but it is a fissionable material, and 238 is a fertile material. Of course, there is a small quantity of uranium-234 is there, 0.0055%, but it is of no use at all. Of course, half-life, see, every uranium is a half-life. Half-life is very long, 4.488, 10 power 9. it is not important here in fission case. So next, see, this is about uranium. The next comes is, in fact, to use uranium in reactors, see, what is required is you have to increase the percentage of uranium-235 because it is a fissile material. So you have to increase compared to uranium-238. You have to increase the percentage. So that process is called as enrichment process. So before making use of uranium as a fuel in the nuclear reactor, so this has to be done. Enrichment process has to be done, and you can enrichment. You can classify to three categories: low enriched uranium, then ISA, low enriched uranium, high enriched uranium. So 235 is important for us. In fact, compared to 238, if you can increase to 3 to 5%, it is called low enriched uranium. See, originally uranium percentage is just 0.7%. Now, by some means, you can increase to 3.5% to get low enriched uranium. And coming to high SA, low enriched uranium, its percentage is 5.20. So, and high enriched uranium is greater than 90%. And different enriched uraniums are used for different purpose. For advanced commercial nuclear power reactors, they make use of low enriched uranium. ISA is used for advanced reactors, and for naval reactors, highly enriched uranium is used. In fact, I have listed the uses of different kinds of enriched uranium in this table. You can just have a look. So going to the next, we have to understand how uranium is extracted from the ore, from the mines.
ಫುಲ್ ಸರ್ ರುದ್ರಸ್ವಾಮಿ ಅವರು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡ್ಬಿಡಿ, ಆವಾಗ ಚೆನ್ನಾಗಿ ಕಾಣಿಸುತ್ತೆ. ಕೆಲವು ಲೋವರ್ ಪೋರ್ಷನ್ ಕಾಣಿಸ್ತಾ ಇಲ್ಲ. F5 ಮಾಡಿ.
F5 ಮಾಡಲ? ಓಕೆ, ಮಾಡಿದೆ. ಅಲ್ಲ, ಕೆಲವು ಪೋರ್ಷನ್ ಪ್ರಾಬ್ಲಮ್ ಆಗ್ತಾ ಇದೆಯಾ?
ಅದೇ ಕೆಳಗಡೆದು ಸ್ವಲ್ಪ ಕಾಣಿಸ್ತಾ ಇಲ್ಲ. ಇಲ್ಲಿ ಓಕೆ ನೋಡಿ, ಯಾಕೆಂದ್ರೆ ಫುಲ್ F5 ಆದ್ರೆ ಫುಲ್ ಆಗ್ಬೇಕು. ಬಟ್ ಏನೋ
F5 ನಲ್ಲಿ ಫುಲ್ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಇದೆ. ಇದು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಇದೆ. ಫುಲ್ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಇದೆ.
ಓಕೆ, ಕ್ಯಾರಿಯನ್ ಸರ್, ಕ್ಯಾರಿಯನ್.
So this is how uranium is obtained. Final stage of uranium to use it for nuclear reactor. So this is the process is followed. Uranium fuel cycle process is followed. So first you have to get the uranium ore, from the mines. This is the first stage. Then you have to mill it. See, you have to do uranium ore is milled into yellow cake. It is done like this. Then yellow cake is turned into uranium oxide. Then it must be converted into gaseous form. Just making use of fluorine, so you can convert UO2 into UF6. Unless you convert into UF6, it is not possible to get uranium in a gaseous form. Unless you make it into gaseous form, you cannot do the enrichment process. So that's why it is always done. Gas is enriched. Now, once you get in the UF6 form, you can certainly enrich this uranium-235. See, then once it is enriched, so then what you can do is you can convert back to uranium oxide. So then comes the next process is pellets. It is obtained in the form of pellets, and then in fact, see, this is how you can see this is the pellets, actually pellets. And then you can put this pellets into fuel rods, and of course once you get a fuel rods, then you can use it for reactors to generate electricity. Once of course you after generating electricity, some fuel is spent fuel. Of course you cannot make use of entire uranium fuel for converting into electricity. Some fuel is left out. That fuel you can use is stored at the power plant, and also you can reprocessing. You can reprocess this fuel and you can make use of it again. Okay, and sometimes that reprocessing will be done many times. And sometimes you can store it in the underground repository. So this is about uranium cycle. This is the final form one gets. Then comes this how to enrich the process, how to get uranium 235 enrichment. There are so many processes. In fact, gas diffusion method is followed here because you have two isotopes, 235 and 238. So you can just use this gas diffusion method. Based on the mass difference, it is possible to get more uranium to, of course, you cannot separate out 238 from 235. It is not, you can do it, but it is not required. So 235 proportion you can increase by this gaseous diffusion method, or you can even use centrifuge method. Okay, centrifuge method is well known, so you can use that also, or sometimes laser separation method is also used, in fact. Okay, so you can use pulse CO2, then you can use Raman converter, convert its wavelength 16 micrometer, and in fact your 235 vibrational frequency, in fact the bonding will be there between uranium and thorium. That bonding frequency matches with the 16 micrometer, and that way, because of resonance, it gets separated from, so to some extent they separate from this, and it is considered to be a very effective, most efficient method. Okay, large scale separate enrichment, you can always do it with the help of the last separation, laser separation method. So and this is how it looks. Enriched uranium, this is how it looks. This is a stockpile of highly enriched uranium. This is how it looks. So this you can use it, in the form of pellets, rods, and you can use it in the reactors. And then comes is how uranium fuel is used. That you can understand in the nuclear plant. So what you can do is, you have to start with natural uranium obtained from the ore, mines, and you have to use the enrichment plant. So then you can get this one, low enriched uranium you can produce. Then you can pass on to this into uranium fuel fabrication plant. Fabrication means pellet form, rod form, all such things we can obtain here. Then some left out low enriched uranium, you can do, of course, you can pass into the reactor to produce electricity. Even this LEO, you can straight away pass on to clandestine enrichment plant, a plant to increase, to get high enriched uranium. This is high enriched uranium is required for weapons, weapons manufacturing. So 90%, enrichment is required to produce, for weapons processing. And reprocessing plant. See, whatever fuel is spent is remaining, that you can send it to reprocessing plant. Again, that once it is done, reprocessing plant is done, you can send back to the same process. You can follow once again. So this is about uranium fuel usage forum. And the most important for nuclear reaction is fission reaction. Nuclear fission. You have to make use of, that too, for uranium 235, what is required is slow moving neutron. Slow moving, fast moving neutron, slow moving neutron. There are two categories. In fact, slow moving neutron energy is very less, equal to 0.025 electron volt. It is equal to the thermal energy of the gaseous molecule. And fast neutron energy will be 2 to 3 MeV. But for fission 235 to take place, what is required is slow neutrons. So this is important. Fast neutrons doesn't produce any fission of 235. Of course, 238, you cannot get the fission of 238 either using slow neutron or fast neutron. Okay, so this is how the process takes place. Once you are near a neutron, it is called thermal neutron. In fact, it's called as thermal neutron. 235 it bombards 235 and you get two fragments, krypton, barium, and you get three fast neutrons. Fast neutrons, of course, you have to convert this, you have to reduce its energy to thermal, that you can always do it by some means. And again, these three neutrons will bombard with three surrounding uranium-235 and thereby you gets multiplied. In fact, you get every uranium-235 undergo you get two fragments and every neutron, gets multiplied. 3, then 9, 27, likewise, see, it continues. This is called chain reaction. It is chain reaction. It takes place within no second. If chain reaction is not controlled, what happens is you get a huge amount of energy releases, and that leads to massive explosion. This is called uncontrolled chain reaction. See, it is used. That principle is used in nuclear bombs. If the chain reaction is controlled, then you can use a controlled energy. The energy releasing, you can use it for peaceful purpose. You can generate electricity in nuclear reactor. Even nuclear reactor is also called as nuclear fire. See, same thing I have shown it here. Okay, same pictures for clarity, more clarity. In fact, how to control chain reaction, that depends on this multiplication factor. See, this is how it is defined. First generation, second generation, if you can maintain every time, one neutron, if you start with one thermal neutron, if you can get even in second generation also after fusion, if you can get one neutron, if you can maintain one neutron, then that ratio between first generation, second generation ratio, if it comes out to be 1, then it is, then you can able to control. Of course, extra neutrons you can allow it to escape. That method they follow. Control chain reaction is a must for this thing. Of course, this is how it looks. A nuclear reactor, this is how it looks. Main components are fuel elements. Of course, you can get in the form of a rod. This is how, these are the rods, in fact. These are the rods, placed between the moderators. Moderators are essential. Uranium-235 rod. Without moderator, you cannot see whatever fast neutrons you get here, you cannot reduce it to thermal neutrons. So therefore you have to make use of moderator. It slows down the fast moving electron. Then controlling unit. You see, this is a controlling unit. The cadmium, boron, they use actually. It is used to slow down the rate of chain reaction. You can always control. You can slow down the neutrons number, and you can even shut down the reactor. See, with the help of this control rod, you can emergency. It is inserted into the nuclear reactor. Thereby, you can stop this thing. And once when the reaction is going on, you have to make use of coolant. Coolant, of course. The coolant is there. Coolant, of course, it is always sent to the nuclear reactor, and so a lot of thermal energy is produced here. This coolant job is, it absorbs and takes away that heat. Into this. This is the channel. See here, the coolant, with a lot of energy flows here, and this is the secondary loop. It flows into the primary loop. Secondary loop, water gets circulated. And in fact, whatever heat is carried by the coolant gets transferred to the secondary loop, and thereby the water gets converted into steam. That steam is passed into the turbine, and that turbine, once turbine is rotated, you can generate electricity. So in fact, see, this same figure I have shown it here. See, this is primary circuit, secondary circuit. In fact, you can use cooling tower to cool whatever steam is produced here in the secondary circuit. You have to cool it. You have to reduce that steam into water. So that same water you can again use it in the secondary circuit. To convert into steam. So that cooling tower, this is separate circuit used to reduce that into cooling. This is how it is done. Of course, See, you have to make use of the shielding also. Shielding is important, which protects the people around the reactor from radiation. So these are, in fact, coolants are water, nitrogen, carbon dioxide. Normally, this graphite and heavy water. H2, there are two kinds of water used in the reactor. One is ordinary water, light water, H2O. And another is heavy water, D2O and graphite. These are the two materials used. Okay, and this is about a nuclear reactor design. Coming to, see, you can always compare your nuclear power plant with the coal power plants. See, in fact, the coal power, see, you can replace coal furnace by nuclear reactor. That's all. The other things remain same. The same steam turbine here and also in both the case generator. Only here it is replaced. Coal furnace is replaced by nuclear reactor. Of course, that water circulation will be there in both the cases. So what is the advantage of using the nuclear reactor or nuclear power plants? In fact, I have listed here 1 kg of uranium-235 is equivalent to 4,500 tons of high-grade coal. So to produce the same amount of energy, so much of coal you have to burn to get same amount of energy. And that leads to greenhouse effect. The nuclear greenhouse gas, carbon dioxide releases so much by burning coal. That problem we can reduce with the help of this. Nuclear fission can release 1 million times more energy than that of coal burn per atom. So this is how we can compare. Nuclear power plant is advantage over coal versus because we can always reduce the gas greenhouse gas. So coming to, see, this is how coal power plant looks. Generally, this is how it looks. Okay, so you will have cooling towers, of course, all the things, I have explained. So much of infrastructures, you have to make use of coal power plant. I think it doesn't require here details. So this is how generally nuclear power plant looks. Okay, see, this is also, see, same, whatever a power plant means, what I explained is nuclear reactor. But in addition to nuclear reactor, you have to make use of so many other infrastructures. So towers, these are the towers, used in nuclear power plant. Coming to, see, this is how nuclear power plant control room, this is how it looks. So this is also, you have to make use of this control room to control everything. And coming to the classification and components of nuclear reactor. See, thermal neutron reactor and fast neutron reactor. Of course, most of the reactors are thermal neutron reactors. Every country is making use of thermal neutron reactors. Of course, every country is making use of uranium-235 as a fuel. So, and you can further classify thermal neutron into light water moderated, heavy water moderated. What do you mean by light water moderated? See here, for moderation purpose, when you are using a fission of uranium-235, fast neutrons are produced. Unless you slow down the neutrons, you cannot get further fission of 235. So every time, you must slow down the fast neutrons. So you have to make use of moderators. Either you can use light water, ordinary water, or heavy water. Okay, of course, I will explain advantages later on. But again, in light water, there are two types. Of course, the boiling water reactors and pressurized water reactors. So there are two. This is how you can classify. And coming to, of course, heavy water reactor, no further classification. Coming to graphite moderators, moderators, there are three types: light water, heavy water, and graphite. Graphite moderated reactors, or again you can classify gas cooled, water cooled, liquid metal cooled. Of course, sorry, it is this liquid metal cold is used in the fast nuclear reactors. Only this thing. See, in fact, I have shown here this table. I have shown what kind of neutron is used. In most of the cases, for all thermal reactors, you have to make use of neutron as a bombarding particle for uranium 235 thermal. Of course, the fuel. Quantity of uranium waste. In fact, for pressurized water reactor. See, in fact, pressurized. I will explain those two things later on. 3 to 5% enriched uranium you have to make use of. Of course, uranium will be in the form of oxides. You have to fuel is this thing, and coolant is H2O. In fact, moderator and coolant both are same in pressurized water reactor. H2O is used. Coming to boiling water, also same thing. But the working principle will differ. See, in fact, all the four components same for both the pressurized water reactor, boiling water reactor. Coming to pressurized heavy water reactor, so you can make use of natural uranium. You don't need to use the enriched uranium oxide, because here in this case what happens, if you make use of ordinary water, in fact, your neutrons, instead of most of the neutrons get absorbed rather undergoing slowdown by ordinary water. Undergoes slowdown if you make use of ordinary oxide. So that's why you have to use that enriched atom. That way you can, to some extent, you can get the fission. Ordinary water can not only can slow down but also absorb more neutrons. That problem you faces both in pressurized water reactor and boiling water. But in the pressurized heavy water reactor, D2O, heavy water, see, you don't have to use it. You see, it doesn't absorb neutrons, thermal neutrons. It only, it slows down the neutrons, fast neutrons. Moderator also you can coolant. See, of course, you can use, one advantage is in all these three cases, you can use same material for both coolant and moderator. Coming to advanced gas cold reactor, it is there it is used 3 to 5% enriched, same thing. Enriched uranium is used. Only thing is instead of using water, carbon dioxide is as a coolant. Graphite, instead of using D2O, graphite is used. Graphite both for light water graphite reactor and for advanced gas cooled reactor, graphite is used as a moderator. Of course, your coolant will differ. One case it is CO2, another case it is H2O. Of course, fast reactor case, you don't have to use any moderator, because you can, fast feed reactor, you can make use of plutonium-239 and it undergoes fission by fast neutrons. Only thing is you must start with this, conversion is there. See, you don't get plutonium-239 naturally. You have to convert 238 into 239. So you have to make use of this enriched uranium oxide or ordinary mixed oxide, mixed uranium and this thing. I will come to that thing later on. Of course, coolant is used is liquid and sodium or lead. Of course, it is available in the liquid form. You can pass into the reactor and you can remove heat from the reactor core. So this is about coming to pressurized water reactor and boiling water reactor. So, see there, the one difference between pressurized water reactor and boiling water reactor. In pressurized reactor, you have two loops. This is actually primary loop, and this is secondary loop. See, of course, this turbine part is common. The turbine generated part is common. Cooling part is common. Only you will have extra loop, in pressurized reactor. But here, no such thing you find here. In fact, so what happens in boiling water reactor? See, your water gets into the reactor, gets boiled. Temperature will be around 350 something. See, it gets boiled, it's converted into steam, and that steam is pass into the turbine straight away directly, and see this generator produce electricity, and and your steam gets condensed. The cooling, okay, see, you use that separate cooling system, and thereby you can convert. Okay, you can condense into water, and that water you can again make use of here. But in this case, what happens is your water gets into the core, and see, and here what happens, see, here it is pressurizer is used. That way, the water, of course, gets heated up, but doesn't convert into steam. It doesn't boil. Comes into the primary circuit, and there, this is called steam generator, is also called as heat exchanger. So here, okay, water gets exchanged. In fact, heat is get exchanged to the secondary circuit, where water is circulating, that converts into steam. So that way, this one okay, difference you find. And advantage in the pressurized water reactor is, okay, it doesn't mix up. Whatever heat is carried by the water doesn't mix up with the secondary circuit, and whatever radiation is carried by the water, it doesn't mix up in the external circuit. But here there is a chance of mixing of gas radiation takes place. That problem, you can avoid with pressurized this thing. So this is about. In both the cases, we are making use of water there, coolant and water. It is common. Only thing is design-wise differ. So coming to the next thing is pressurized heavy water reactor. What I said is pressurized water reactor, ordinary water reactor. This is you are now making use of heavy water. Of course, see, this is called pressurized heavy water reactor. Is also called as CANDU. This is the reactor, okay, developed by Canadians. In Canada, first time, see, CANDU, it is called as CANDU means Canada Deuterium Uranium. Developed first time in Canada. See, this is the reactor core is a horizontal cylinder. It is called as calendaria. Here, which this is how you can put the bundles in a horizontal way, and anytime while it is in operation, you can even replace the bundles. But in previous two cases, unless you shut down, you cannot replace the fuel rods. But here in this case, it is, of course, heavy water. It serves as both coolant and moderate. First time it is introduced by Canada. Okay, in Canada. Coming to advanced gas cooled reactor. See, this is a unique advanced gas cooled reactor. Of course, it is an improved version of Magnox reactor developed first time by UK. It is the only country operates even now also. This kind of reactor you don't find anywhere in the world. So it is operated by them. They are making use of carbon dioxide as a coolant and graphite as a moderator. They are not making use of H2O. Okay. So of course, whether it is except boiling water, all other reactors, you can find two loops: primary loop, secondary loop. Okay. See, because the safety system comes into picture. So it is always better if you make use of two separate loops. Okay, one for heat. Okay, one for taking away heat from the core, another to transfer to the external circuit. So this is developed by UK. Okay, and now also it is used by them only. So this is about this thing. And coming to light water graphite reactor. See, this is the reactor, uses, okay, of course, even the previous case also they use graphite reactor. Light water, these people, okay, it is developed by Soviet Union. First time there was a minimal technology transfer from Western bloc countries. Without depending on other countries, they just developed this reactor on their own. Of course, they make use of water as a coolant. Of course, graphite as a moderator. So here, see, of course, you will have two units here. See, two units clubbed together here. Here also you can send your water from here and gets converted. Okay, steam. In fact, it flows like this. In the reactor core, rods will be there. Graphite. See, in fact, these are graphite portions. Graphite rods are there, and gets converted. Heat is produced here. These are block lines, shown represent control rods. Of course, this is another unit used. Same process you can expect to on this also. So what is used? See, they are making use of. They used this technology first time. Okay, and now also they are making use of this reactor. Okay, coming to the next part. It is the fast build reactor. It is not a thermal reactor. See, you can make use of fast neutrons here. In fact, see, what you have to do is you can make use of here. This is the reactor core. What you can, your starting material is uranium. In fact, you can use this uranium 238, natural uranium you can make use of here. Of course, sometimes they make use of uranium, plutonium, mixed oxide as the initial fuel in the core. Of course, small amount of 235 is also used to undergo fission to produce thermal neutrons. Because thermal neutrons, you is required to produce fast neutrons. Unless you make use of thermal neutrons, you cannot think of fission of uranium 235. Unless you think of fission of 235, you cannot think of fast neutrons. But for fast breed reactor, what is required ultimately? Fast neutrons. So what is, once you produce fast neutrons by fission of 235, what you can do is, in fact, the 238, okay, you can use it in this fuel, you can use it as a blanket, which surrounds the fuel, original fuel like uranium 235 and uranium plutonium oxide. So once these fast neutrons are produced, what happens? It undergoes nuclear transmutation. In fact, I have shown here how the neutron, once the fast neutron bombards with 238, it converts into uranium 239. It's absorbed. The neutron gets absorbed. It becomes uranium 239. In fact, I have shown this also offline. Very short offline. See, next, this uranium, again, one more neutron gets absorbed and it becomes 239 and you get beta. See, this is actual beta decay. And that beta decay process, it gets converted into this thing. And plutonium, ultimately, you get the plutonium 239. This is how the plutonium 239 is produced. And see, this is the plutonium 39. Once it is produced, it makes use of fast neutrons, and that becomes a 240 plutonium. And of course, you get here also undergoes fission. So these are two fission fragments. You get 3 neutrons. You get it. Out of 73% undergoes fission, and remaining 27%, neutrons get absorbed by plutonium. Okay, that thing is there. Of course, this is gamma. Gamma is also produced here. And here, two things you have to, why it is called as fast build reactor. See here, in the fast build reactors, not only you can produce plutonium 239, that plutonium 239, you have to make use it, you have to get the fission of 239 to get the nuclear energy. Fission and production, both are required, but you can make arrangement in such a way that you can produce more number of plutonium 239 than undergoing fission. That is breed. You can always think of breeding of plutonium 239. Unless you think of breeding of plutonium 239, what happens is ultimately your fuel will get exhausted. You must think of producing more number of 239 than undergoing fission. That process always done it here, of course. See, this reactor is now is developed, is operated only in Russia. Nowhere else, it is operated. Of course, India is now in fact, they are trying to do experiments on this, prototype. They are implementing in Kalpakam, and they are trying to. Okay, it is not yet it is commissioned. It takes some more time. Once commissioned, India will only be the second country after Russia to have a commercial operating. See, it is important. Commercial is important. Other countries, operating fast reactors, but they are not important. So Russia has two fast build reactors. They are making use of. India, I think, in short span, they can also achieve this. Obtain this thing, fast build reactor. So this is how it looks in the core. So in fact, core next comes. This is the primary circuit. Sodium is sent sodium sent from here to here, goes to the prime. This is a primary loop. Again it goes to secondary loop. Okay, there this heat exchanges. Sodium carries heat and exchanges heat to secondary loop where water is flowing. So that water converts into steam. See, for turbine, turbine to rotate. You can just depend only on ordinary water. But coolant, you have to select. You can select any of the materials, like the sodium, carbon dioxide, heavy water, or H2O. Okay, so this is how you will have two second loops for sodium coolant to flow. So this is how it looks. So next comes this. Now we have to think of pros and cons of nuclear power. The pros means it is a low cost energy, reliable power source, creates jobs, zero carbon emission, high energy density. Okay, that is, of course, you make use of less fuel and produce high amount of nuclear energy. Coming to cons, environmental impact. See, of course, there is radiation. You have to protect carefully. Otherwise, that leads to environmental problem. Of course, to generate nuclear energy, you have to make use of so much of energy. Water usage is very much. All our plants are established very close to the water sources. So risk of nuclear accidents, that problem is also there. We must be very careful. Radioactive waste, of course, radioactive waste it is unavoidable. But you must think of how to dispose of this radioactive waste. Next comes is non-renewable. It is not a non-renewable energy. That is unlike solar. This is a non-renewable energy source. This is how you can think of pros and cons. Coming to the next three-phase nuclear program. In fact, India is planning three-phase nuclear program. Why we have to depend on three-phase nuclear program? Because uranium availability in India is just 2% compared to all other rest of the countries. Our availability in uranium is just 2%, and we are procuring uranium from outside. So it is a costly affair. But the thing is, if you just look into this world chart, thorium reserve chart, you can find here India reserve is vast. In fact, 13% vast compared to any other country. It's vast. It has a vast thorium reserve. Of course, next comes is Brazil, Australia, 9%. But you can make this thorium. Only thing is, only problem with thorium is it is not a fissile material. You have to convert it to fissile material. So it is planned. It is already planned. India has planned to have to make use of thorium. So this is the reserve part. How uranium is formed. See, this is uranium-232. Once you make use of uranium-232 in a reactor, it absorbs fast neutrons. In fact, fast neutrons converts into thorium-233. It absorbs one neutron and then undergoes beta. Twice it undergoes beta. Protactium, twice it, and finally it goes to uranium-233. This is how it converts, and your 233 is a fissile material. This you can make like your plutonium-239, uranium-233 is a fissile material. You can make use of it, and of course that you can use it for fission. The 233-92 fission. Make use of neutrons, fast neutrons, undergo fission. Okay, of course here you get 94% fission and 6% absorption is there. So, but the thing is, it is not implemented, it is planned. Say three-phase nuclear program is planned with the aim of utilizing the vast thorium reserves. In the first phase, second phase, third phase. These the three phases are planned. In first phase, you see this is like your fast-build reactor. Fast-build reactor you can make use of here. In fact, you start with uranium-235, you bombard with thermal neutrons, and you get say uranium. Okay, that fast neutrons we can convert, use it to convert 238, then plutonium-239, then for you get that this is a first phase. This is a fast-build reactor phase. Second phase, whatever fast neutrons you produce by bombardment of plutonium-239. You can make use of it. You can use thorium-232 as a blanket. Okay, just you can surround. It is surrounded these materials, uranium and material, and thorium absorbs the neutrons, and 233 ultimately you get it. And this second process continues here also. Here, of course, second and third phase difference is this will not be will not be there here. TM233, undergoes fission. Okay, neutrons, whatever neutron you get, this thorium-232 undergoes the 230, it undergoes transmutation. In fact, it's called transmutation. Finally, 233 you get it, fission. This process, this is a three-phase process. It is planned. In fact, Baba envisaged this process, but it is not yet completed. It takes some time. I don't know when it will start. It is the program planned only in India. Okay, coming to now we have to think of a list of nuclear power reactors. Under operation. In fact, we have 7 nuclear power plants with a total of 24 nuclear power reactors. Total in India we have 7 nuclear power plants. Total 24 nuclear power reactors. In fact, Tarapur Atomic Power Station. There are 4 units. This is established in 1968. Unit 1 and 2 boiling water type, and 3 and 4 are pressurized heavy water reactor. India's first nuclear power reactor plant, oldest operational unit. Next, Rajasthan Atomic Power Station. There are 6 units. 73 it was established. The pressurized heavy water reactor is used there. Of course, it is known for consistent performance and one of the India's largest. The next, Madras Atomic Power Station, Tamil Nadu, Kalpakkam. 84 it is established. The type of reactor is PHWR, and first indigenously constructed nuclear plant. Indigenously, without depending on any other country. This was constructed indigenously. The Narora, Uttar Pradesh. Okay, located on the banks of Ganges, known for its safety system. Kaiga, in fact, 4 is there. Built-in seismic sensitive zone with advanced safety features. Of course, Kaiga is seismically sensitive third zone, less risky zone compared to first zone. It is there. So 4 units are operating. 2000 it is established. Kakrapur Atomic Power. 93 it is established. Kudnakulam Nuclear Power Plant. In fact, Russia, we are depending on Russia. See, they have, taken their help, and it is under operation. Of course, it is called as water energetic reactor, VVER. The meaning of VVER is Vodani energetically reactor, Russian word. Okay, it is they make use of water as a coolant. Water, and in this case, water. Okay, so this is how it is used. Okay, Kudakulam, of course, it is under operation. So total, in fact, total Okay, we are generating 8,080 megawatt electricity from all these 7 nuclear power plants. So coming to world nuclear reactors, total number of reactors in the world is 449. 449. The United States of America of course, have highest number of reactors operating. Of course, see, is in fact 7th place. We are in 7th place. 24 reactors we are operating, and okay. So this is about reactors. Coming to waste disposal. See, this is the thing. Nuclear waste disposal. See how we are disposing our nuclear waste. See, okay, what happens is, nuclear waste, see, 96% of the nuclear waste is recycled and reprocessed and used it again and again. Okay, and only 4% radioactive waste containing radiation. See, you cannot do any reprocessing. You must make use of a proper disposal. Nuclear waste. Okay, how it is done? It is done deep underground up to 1 kilometer. Power plant below 1 kilometer below, you have valves and tunnels for storage. So you have to take that radiation into that deep, and you have to store it in the walls and tunnels, and thereby you can save from the radiation. That is one thing. See, these facilities are aimed to offer long-term protection. So this is how the disposal is done. And the last one is security. Security measures are very strict because protecting the plant from sabotage and attack is important to protect people from and the environment. And more details about security plans are not available to the public. That is another way the plants are kept secure. So this is about my talk. So thanks for your patience hearing. So I will take up some questions from you.
Okay. Thank you very much, Dr. Rudraswamy.
Thank you, sir.
So ಯಾವ್ದು ಪ್ರಶ್ನೆಗಳಿದ್ರೆ ಕೇಳಬಹುದು. ನಿಮ್ಮ ಕೈ ಎತ್ತಿದ್ರೆ ಸಿಂಬಲ್ ಅವಾಗ 1 by 1 ವಿಗೆ ಆಸ್ಕ್. ಈಗ ದಯಾನಂದ್ GN ಅವರು ಕೇಳಬಹುದು ಪ್ರಶ್ನೆ. ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಅನ್ಮ್ಯೂಟ್, ನಿಮ್ಮ ಮೈಕ್ರೋಫೋನ್ ಮ್ಯೂಟ್ ಆಗಿದೆ. Unmute ಮಾಡ್ಕೊಳ್ಳಿ.
Am I audible?
Okay.
Yes, sir. Yes, sir.
Yes. So very nice talk, and good afternoon to all of you. We are past 12 o'clock, I think.
Yes, sir.
Yeah. We started before 12, but very informative, and as somebody pointed out already, the quality of slides is really very good.
Thank you.
In some slides, it's giving a three-dimensional effect very nicely. On a 2D screen. The question I have is regarding the safeties. You mentioned that, for example, in Kaiga, some advanced safeties have been put in place.
Yes, sir.
And, so if you can throw more light on that, or else you can also share it later. But if you have the idea of the advanced safeties that have been put in place in Kaiga, for example, and even generally in the recent power plants, because India has a good track record of safety, I think.
Yes,
that's what my understanding is.
Yes, correct.
So if you can share some of your knowledge in this area, it will be good. Thank you.
They are taking all kinds of measures to safeguard people from all kinds of hazards. As you said, India is having a very good track record. So far, there is no such major accident took place, fortunately, and no such problem. In fact, that is the thing. I can say I can get you more details about this thing. As I said in the previous slide, this is how. In fact, this is how. See, they are following the disposal problem. See, they always make use of valves and tunnels, 1 kilometer below the plants, and burying the dispose. That to 4% of the nuclear waste is burying below, and they are not. Yes, sir.
ಅವ್ರು ಕೇಳ್ತಾ ಇರೋದು ಸೆಕ್ಯೂರಿಟಿ ಅಂತ, ಸೇಫ್ಟಿ ಅಂತ, ಸೆಕ್ಯೂರಿಟಿ
Safety. I'm asking about the safety particularly. Let me be more specific. For example, seismic zone. Kaiga is in this seismic zone. So, what are the safety measures in the design? For example, so these are the questions that I thought it may be relevant to the public also because
Yes, sir. Seismic
because the
zone
concerns.
3 is not very risky zone. See, you can classify 1, 2, 3. See, third zone, see, there is, of course, there is no other go for Kaiga, no, you have to establish your nuclear reactor there. To choose a reactor, Kaiga for reactor, you have to make use of it, but it is classified seismic 3 zone. See, no such seismic activity, major seismic activity is taking place there. Of course, they are taking all kinds of safeties. The details I can give you later on.
Yeah, maybe later we can.
Later on, I can, no problem.
No problem. I'm just alerting.
Certainly, I'll give you details.
Thank you very much. Thank you. Nice talk. Once again, let me compliment.
Thank you, sir.
Thank you. Let us move on to another question.
This is
Yes, sir. Tell me, sir.
as our friend Mr. Dayanand mentioned,
Yes,
in
sir.
fact, beautiful presentation with very clear slides,
Yes.
containing lot of information and well prepared, sir.
Yes,
We are really congratulative and thank you very much for your excellent talk.
Thank you, sir. Thank you for your.
My concern is, it's actually not a doubt concern. See, the nuclear waste, 4% of that which are all radioactive, am I right?
Correct.
So the 4% of the garbage, nuclear garbage, I tell you, it's actually radioactive.
Correct.
Even if you bury it under a depth of, let's say, 1 kilometer, and for future generation, will it not be a threat to the future generation?
Maybe I don't think, see, they taking into consideration all these concerns. See, this is how they have, taken this strategy and did the, 1,000 kilometer maybe is sufficient to, even your lead blocks, can prevent 100%. In fact, 1 kilometer is not a small distance. I think this 4% you can certainly protect from hazard. That's what. But nothing has happened so far. As far as I know, any country you take, that radiation hazard problem is not taken place anywhere. I think there are
one more thing is,
yes,
when
sir.
comparing this thermal power plant and also the nuclear power plant, you are telling that nuclear power consumes more water. Even thermal also consumes more water. So out of the two, which is more water, let's say, this thing, consuming more water? Because thermal also based on water, this thing only.
Of course. Here what happens, coolant, of course, in both the case, coolant, in fact, what happens in nuclear reactor, you are making use of water as a moderator. See, that is an additional thing you find it in nuclear reactor, but not in coal. Coal is only, water is used as a coolant. I think more water consumes in nuclear power plants rather than coal power plants.
No, thermal plant, then water is converted to steam. Steam runs the turbines, right?
Of course.
It's actually based on water. Yeah.
See, water is required for both the cases.
Yeah.
Only thing is nuclear power plant. You can that green gas. See, you can avoid using this. Of course, it has some, but so far no such problems we have faced from reactors. We are operating 24 reactors.
The last question, sir. Last question.
Yes, sir. Yes.
Out of 24 units, only 7 are operating. Why the others are idling? I didn't understand.
No, it is the total, all the 24 reactors, only one reactor is now decommissioned because it has become very old. But all the 24 reactors, are working. Sir, 8,080 is megawatt capacity. No, it's not just 7 plants, sir. 7 plants we have.
Plants are the reactors.
Every plant has so many reactors, units.
I see.
Putting together all 7 plants, you will have 24 reactors.
Oh, I understand.
Sir,
I thought it
Yeah.
was 24.
no.
No.
Sir, 7 plants are under construction.
No. They
That's
all
now-
already constructed.
sir, all are working, sir. All 7 plants.
No.
No.
What I say
What's
that number 7 are under construction now, other than the 25. Yeah.
No.
No, sir. They're all
Okay, no, what
these are not.
there are seven locations you have got power plants. I mean nuclear power plants. Out of in all the 7 places, all the units together 24. That's what I'm
Yes,
saying.
you are right, sir. Just see, please see the slide, sir. Please see the slide. See, these are the 7 power plants, the locations. Displayed
Location 7, and out of which 24 units are working. Yeah.
24, okay, 24 units. Okay, every location you will have more than one reactor, more than one unit.
Okay, let's move on to next question.
ಅಲ್ಲ ಸರ್, ನಾನು ಹೇಳಿದ್ದು
ಹೇಳಿ ಸರ್.
24 ಅಲ್ಲದೆ ಇನ್ನು 7 ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ ಅಂತ ಹೇಳಿದ್ರೆ.
ಅದಿದೆ
ಅದು ಹೇಳಿ.
ಡೆಫಿನೆಟ್ ಆಗಿ ಇದೆ. ಅದನ್ನ ಇಟ್ ಇಸ್ ನಾಟ್ ಟೇಕನ್ ಇನ್ ಟು ಕನ್ಸಿಡರೇಷನ್. ಡೆಫಿನೆಟ್ ಆಗಿ ಇಟ್ ಇಸ್.
Okay, move on to next question. ಈಗ ನನಗೆ ಒಂದ್ 2-3 ಬಹಳ ಸಿಂಪಲ್ ಕ್ವಶನ್ಸ್ ಇದೆ.
ಹೇಳಿ ಸರ್.
ಈಗ ಒಂದು ದೊಡ್ಡ ಕೂಲಿಂಗ್ ಟವರ್ಸ್ ಇರ್ತಾವಲ್ಲ, ಇದು ರಿಯಾಕ್ಟರ್ಸ್ ಹತ್ರ, ಔಟ್ ಆಕ್ಚುಲಿ ಏನ್ ವರ್ಕ್ ಮಾಡ್ತಾರೆ? ದೊಡ್ಡ ಕೂಲಿಂಗ್ ರಿಯಾಕ್ಟರ್ಸ್ ಇರ್ತದಲ್ಲಿ ಬಾಡಿ ಇನ್ಸೈಡ್ ಆಗಿರುತ್ತೆ ಸ್ವಲ್ಪ ಹೇಳ್ತೀರಾ?
Water goes into the whatever steam is there, it gets into the reactor, that cooling tower, gets cooled there, and condensing takes place, and out the exit point ಅಲ್ಲಿ what you get is water. And the cooling tower ಇಂದ you can always reduce the temperature of the steam.
ದೊಡ್ಡದಾಗಿ ಹಾಕಿರ್ತಾರೆ ಅಂತ ವೈ
ನೋಡಿಲ್ಲ ಅಂದ್ರೆ ಸರ್, it is difficult to cool. It's a large amount of steam, generating. You must have to use large cooling towers only.
So what I understand is, water absorbs heat from the reactor, gets converted into steam, that is used to run the turbine. So that's
Yes,
the coolant job.
That is correct. You are right, sir.
Yeah.
Then that steam,
Yes.
whatever steam is left out, it must be reused.
Cooled and again sent back.
So you have to cool it back. You have to cool it using cooling tower. You have to send it back to the reactors. Core.
Yes, sir.
Yes.
ನೆಕ್ಸ್ಟ್ ಕ್ವಶನ್ ಪ್ಲೀಸ್. ಈಗ KS ಮಲ್ಲೇಶ್ ಅವರು ಕೇಳ್ತಾರೆ, ಪ್ಲೀಸ್ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಬಿಟ್ಟು ಕೇಳಿ. ಮಲ್ಲೇಶ್ ಅವರು, ನಿಮ್ದು ಮೈಕ್ರೋಫೋನ್ ಆಫ್ ಆಗಿದೆ. ಓಕೆ, ನಾವು ಈಗ ಕೇಳಿ ಮಲ್ಲೇಶ್ ಅವರು. ಪ್ರೊಫೆಸರ್ ಮಲ್ಲೇಶ್ಗೆ ಲಾಸ್ಟ್ ಕ್ವಶನ್ ಕೇಳ್ಬೋದು? ಕೇಳಿಸ್ತಾ ಇಲ್ಲ. ಪ್ರೊಫೆಸರ್ ಮಲ್ಲೇಶ್ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? ಕೇಳಿ.
ಹೇಳಿ ಸರ್. ಪ್ರೊಫೆಸರ್
ಚೆನ್ನಾಗಿದೆ ವಿವರಣೆ. ಒಂದು 2 ಅಂಶ ಕಲಿತಾ ಇರೋರ ದೃಷ್ಟಿಯಿಂದ ನೀವು ಸ್ವಲ್ಪ ಅದನ್ನ ವಿಷದಪಡಿಸಬಹುದಾಗಿತ್ತು ಅನ್ಸುತ್ತೆ. ಒಂದು, ನ್ಯೂಟ್ರಾನ್ಗಳನ್ನ ನಿಧಾನ ಮಾಡೋದು ಕಾರಣ ಏನು? ಅದರ ವೇಗ ಜಾಸ್ತಿ ಯಾಕೆ ರಿಯಾಕ್ಷನ್ ಆಗೋಲ್ಲ? ಒಂದು ಕಾರಣ. ಇದಕ್ಕೆ ಉತ್ತರ ಹೇಳಿದ ನಂತರ ಇನ್ನೊಂದು ಪ್ರಶ್ನೆ. ಅದು
ಇವಾಗ ಹೇಳ ಸರ್, ಅದಕ್ಕೆ ಆನ್ಸರು. ಇವಾಗ ಏನಾಗುತ್ತೆ ಅಂತಂದ್ರೆ, ಇವಾಗ ಕ್ಯಾಪ್ಚರ್ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ ಅಂತ ಬರುತ್ತೆ. ಇವಾಗ ಯುರೇನಿಯಂದು ಕ್ಯಾಪ್ಚರ್ ಆಗ್ಬೇಕಾದ್ರೆ ಸ್ಲೋ ನ್ಯೂಟ್ರಾನ್ಸ್ ಅದೆಲ್ಲ ಸ್ಟಡಿ ಮಾಡಿದ್ದಾರೆ. ಫಾಸ್ಟ್ ನ್ಯೂಟ್ರಾನ್ಸ್ ನೆವರ್ ಗೆಟ್ಸ್ ಕ್ಯಾಪ್ಚರ್ಡ್ ಬೈ ಯುರೇನಿಯಂ 235. ಅದು ಇಂಟ್ರಾಕ್ಟ್ ಆಗಿ ಸಿಂಪ್ಲಿ ಕಮ್ಸ್ ಔಟ್ ಸರ್. ಇಟ್ ಡಸಂಟ್ ಇಂಟ್ರಾಕ್ಟ್ ವಿತ್ 235. ಓನ್ಲಿ ಸ್ಲೋ ನ್ಯೂಟ್ರಾನ್ಸ್ ಕ್ಯಾನ್ interact, then causes fission.
ಹೈಸ್ಕೂಲ್ ಅಥವಾ 10ನೇ ಕ್ಲಾಸಿನ ಮಕ್ಕಳ ಲೆವೆಲ್ ಹೇಳೋದು.
ಹೌದು ಸರ್.
ನ್ಯೂಟ್ರಾನ್ ನಿಧಾನವಾಗಿದ್ದಷ್ಟು ಚಲಿಸಿದಷ್ಟು ಆ ಜಾಗದಲ್ಲಿ ಅದರ ಯುರೇನಿಯಂ ಜೊತೆ ಅದು ಇಂಟ್ರಾಕ್ಟ್ ಆಗುವ ಸಾಧ್ಯತೆ ಹೆಚ್ಚಿರುತ್ತೆ.
ಹೌದು. ಈಗ ಒಂಥರ ಡ್ಯಾಮ್ ಅಲ್ಲಿ ನೀರು ಫಾಸ್ಟ್ ಆಗಿ ಹೊರಗಡೆ ಬಂದ್ಬಿಡುತ್ತೆ. ಸ್ಲೋ ಇದ್ರೆ ನೀವು ಸೇಫ್ ಮಾಡಬಹುದು ಅಂತ ಅನ್ನೋದಿರುತ್ತೆ. ಆ ತರ ಇದು ಹಂಗೇನೆ. ರಿಯಾಕ್ಷನ್ ಆಗ್ಬೇಕು ಅಂತಂದ್ರೆ ನೀವು ಸ್ಲೋ ನ್ಯೂಟ್ರಾನ್ ಯೂಸ್ ಮಾಡ್ಬೋದು. ಅದು 235ಗೆ.
ಇನ್ನೊಂದು ಪ್ರಶ್ನೆ, ಎನರ್ಜಿ ರಿಲೀಸ್ ಆಯ್ತು ಅಂದ್ರೆ ಯಾವ ರೀತಿ ರಿಲೀಸ್ ಆಯ್ತು?
ಅದನ್ನ
ಗಾಮಾ ರೇಸ್ ಬರ್ತವೆ, ಫ್ರಾಗ್ಮೆಂಟ್ಸ್ ಬರ್ತವೆ.
ಕರೆಕ್ಟ್.
ಜಾಸ್ತಿ ಎನರ್ಜಿ ಬಂದದ್ದು ಯಾವುದರಿಂದ ಅಂತ ಹೇಗೆ ತಿಳ್ಕೊಳ್ಳೋದು?
ನೋಡಿ ಸರ್, ಈಗ ಇಲ್ಲಿ ಇಲ್ಲೊಂದು ಸ್ಲೈಡ್ ಇದು ತೋರಿಸ್ತಾ ಇದೆ, ನೋಡಿ ಸರ್, ಅದು ಕ್ಯೂಮ್ 235 ಒಂದು ರಿಯಾಕ್ಷನ್ ತೋರಿಸ್ತಿದೆ ನೋಡಿ, ಫಿಷನ್ದು ಕಾಣಿಸ್ತಾ ಇದೆ ಸರ್?
ಹಾ, ಕಾಣುತ್ತೆ.
ನೋಡಿ, ಇದು ಒಂದು ನ್ಯೂಕ್ಲಿಯರ್ ಫಿಷನ್ ರಿಯಾಕ್ಟ್ 235-92 ನ್ಯೂಟ್ರಾನ್ ಬೇರಿಯಂ ಕ್ರಿಪ್ಟಾನ್ ಆಗಿ 2 ಫ್ರಾಗ್ಮೆಂಟ್ಸ್ ಬರುತ್ತೆ, 3 ನ್ಯೂಟ್ರಾನ್ಸ್ ಬರುತ್ತೆ. ಇವಾಗ ಇಲ್ಲಿ ಹೇಗೆ ಅಂತಂದ್ರೆ ಸರ್, ಈ 2 ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ಅಲ್ಲಿರೋ ಟೋಟಲ್ ಮಾಸ್, ಅಟಾಮಿಕ್ ಮಾಸ್, ಇದು ರೈಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ ಅಲ್ಲಿರೋ 3 ಪಾರ್ಟಿಕಲ್ದು ಟೋಟಲ್ ಮಾಸ್ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ ಇದರ ಮಾಸ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ, ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ ಇರೋ ಮಾಸ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ, ಇದು ಕಡಿಮೆ ಇದೆ. ದಿ ಡಿಫರೆನ್ಸ್ ಆಫ್ ಮಾಸ್ ಏನಾಗುತ್ತೆ ಅಂತಂದ್ರೆ, ಮಾಸ್ ಇಟ್ ಈಸ್ ಲೂಸಿಂಗ್ ದಿ ಮಾಸ್ ರಿಯಾಕ್ಷನ್ ಇದೆ, ಆ ಮಾಸ್ ಅಪಿಯರ್ಸ್ ಇನ್ ದಿ ಫಾರ್ಮ್ ಆಫ್ ಎನರ್ಜಿ. E = mc² ಫಾರ್ಮುಲಾ. ಒಂದು 200 MeV ಅಷ್ಟು ಎನರ್ಜಿ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ ಪ್ರತಿ ಒಂದು ಫಿಷನ್ ಇಂದ. ಒಂದು ಯುರೇನಿಯಂ
ನೀವು ಹೇಳ್ತಾ ಇರೋದು ಅರ್ಥ ಆಯ್ತು, ಆದ್ರೆ ಬಂದಂತ ಎನರ್ಜಿ ಯಾವ ರೂಪದಲ್ಲಿ ಇರುತ್ತೆ?
ಥರ್ಮಲ್ ಎನರ್ಜಿ.
ಅದೇ ಅದು ಯಾವ್ದ್ರಲ್ಲಿ? ಈಗ ನ್ಯೂಟ್ರಾನ್ ಬರುತ್ತೆ ಅಂತೀರಿ, ಫಿಷನ್ ಫ್ರಾಗ್ಮೆಂಟ್ ಗಳು ಬರುತ್ತೆ ಅಂತೀರಿ, ಇದೆಲ್ಲ ಯಾವ್ದ್ರಲ್ಲಿದೆ ಆ ಎನರ್ಜಿ ಅಂತ ನಾ ಕೇಳ್ತೀನಿ.
ಈಗ ಇನ್ನೊಂದು ಸರ್, ಇನ್ಫ್ಯಾಕ್ಟ್ ಗ್ಯಾಮಾಸ್ ಆಮೇಲೆ ಗ್ಯಾಮಾಸ್ ಕ್ಯಾರಿ ಸಮ್ ಎನರ್ಜಿ. ಇನ್ಫ್ಯಾಕ್ಟ್ ವರ್ಕೌಟ್ ಮಾಡ್ಬೋದಲ್ಲ ಗ್ಯಾಮಾಗಳು. ಈ 200 MeV ಏನ್ ಬರ್ತಾ ಇದೆ, ಆ 200 MeV ನಲ್ಲಿ ಯಾವ್ಯಾವ್ದ್ರಿಂದ ಎಷ್ಟೆಷ್ಟು ಎನರ್ಜಿ ಬರುತ್ತೆ, ಎಷ್ಟೆಷ್ಟು ಕ್ಯಾರಿ ಮಾಡುತ್ತೆ ಅನ್ನೋದೆಲ್ಲ ಬರುತ್ತೆ. ಥರ್ಮಲ್ ಎನರ್ಜಿ ಎಷ್ಟು ಬರುತ್ತೆ ಅದೆಲ್ಲ ಬರೀ ಅದೊಂದೇ ಬರಲ್ಲ, ಥರ್ಮಲ್ ಒಂದೇ ಬರಲ್ಲ. ಗ್ಯಾಮಾ ಆಲ್ಸೋ ರಿಲೀಸಸ್ ಫಾಸ್ಟ್. ಇದರಲ್ಲಿ ಇದು ಈ ಎನರ್ಜಿಗಳೆಲ್ಲ ಬೇರೆ ಬೇರೆ ಪಾರ್ಟಿಕಲ್ಸ್ ವಿಲ್ ಕ್ಯಾರಿ ದಿ ಎನರ್ಜಿ. ಬಟ್ ವರ್ಕೌಟ್ ಥಿಯರಿಟಿಕಲ್ ಆಗಿ ನಾವು ವರ್ಕೌಟ್ ಮಾಡಿದಾಗ 200 MeV ಯಾವ್ಯಾವ ಪಾರ್ಟಿಕಲ್ಸ್ ಶೇರ್ ಮಾಡುತ್ತೆ ಅನ್ನೋದು ಅದಿದೆ ವರ್ಕೌಟ್ ಮಾಡೋದು.
ಸಾಕು. ಬಹಳ ಜನ ಪ್ರಶ್ನೆ ಕೇಳ್ತಾ ಇದ್ದಾರೆ, ನೀವು ದೊಡ್ಡದಾಗಿ ಹೇಳ್ತಾ ಹೋಗ್ಬಿಟ್ಟು ಅದೇ ಲೆಕ್ಚರ್ ಆಗ್ಬಿಡುತ್ತೆ. ಈಗ ನೀವು ನ್ಯೂಕ್ಲಿಯರ್ ರಿಯಾಕ್ಷನ್ ತೋರ್ತಾ ಇದ್ರಲ್ಲ, ಯಾವ್ದು ಗ್ಯಾಮಾ ರೇಡಿಯೇಷನ್ ಇಲ್ವಲ್ಲ, ಸೊ ಇಟ್ ಇಸ್ ವೆರಿ ಹಾರ್ಡ್. ಬರೀ ಥರ್ಮಲ್ ಎನರ್ಜಿ ತಡಿ, ನಮ್ಮ ಪ್ರಶ್ನೆ ಕೇಳ್ಬಿಡಿ. ಅಲ್ಲಿ ನೀವು ರಿಯಾಕ್ಷನ್ ಬಂದಿದ್ದೀರಲ್ಲ, ಅದ್ರಲ್ಲಿ ಗ್ಯಾಮಾ ಕಾಣೋದೇ ಇಲ್ಲ. ಆದ್ರಿಂದ ಇದು ವೆರಿ ಸೇಫ್ ಅನ್ಸ್ಬಿಡುತ್ತೆ. ಬರೀ ಥರ್ಮಲ್ ಎನರ್ಜಿ ಬರ್ತಾ ಇದೆಯಲ್ಲ, ವೆರಿ ಪ್ರಾಬ್ಲಮ್ ಆಫ್ ರೇಡಿಯೋ ಆಕ್ಟಿವ್ ಇದು ಡ್ಯಾಮೇಜ್ ಅಂತ ಅನಿಸ್ಬಿಡುತ್ತೆ. ಗ್ಯಾಮಾ ರೇಡಿಯೇಟಿವ್ ಇಲ್ವಲ್ಲ, ಬೇರಿಯಂ, ಕ್ರಿಪ್ಟಾನ್, ನ್ಯೂಟ್ರಾನ್ ಅಂಡ್ ಎನರ್ಜಿ.
ಗ್ಯಾಮಾ ಕ್ಯಾರೀಸ್ ಸಮ್ ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿ.
ಗ್ಯಾಮಾ ಇಲ್ವಲ್ಲ, ತೋರಿಸಲ್ಲ
ಇಲ್ಲಿ ತೋರಿಸಲ್ಲ ಸರ್. ನಾವು ಇಲ್ಲಿ ಎನರ್ಜಿ ಎಷ್ಟು ರಿಲೀಸ್ ಆಗುತ್ತೆ ಅಂತ ಅಷ್ಟೇ ಹೇಳೋದು. ಬಟ್ ಅದನ್ನ ಸ್ಪ್ಲಿಟ್ ಮಾಡಿ ಯಾವ್ಯಾವ ಪಾರ್ಟಿಕಲ್ಸ್ ಎಷ್ಟೆಷ್ಟು ಎನರ್ಜಿನ ಶೇರ್ ಮಾಡ್ಕೊಳ್ಳುತ್ತೆ ಅನ್ನೋದನ್ನ ಸಪರೇಟ್ ಆಗಿ ತೋರಿಸ್ಬೋದು. ಅದನ್ನ ಹೇಳಿಲ್ಲ.
ಬಿಡಿ ಅಷ್ಟೇ, ಒಂದ್ ಸೆಂಟೆನ್ಸ್ ಲೆಕ್ಚರ್ ಕೂಡ ಹೋಗ್ಬೇಡಿ. ಪ್ರಶ್ನೆ ಉತ್ತರ ಬಹಳ ಜನ ಕಾಯ್ತಾ ಇದ್ದಾರೆ ಪ್ರಶ್ನೆ ಕೇಳೋದಕ್ಕೆ. ಓಕೆ,
ಹೇಳಿ ಸರ್.
ಸರ್, ತುಂಬಾ ಇಂಟ್ರೆಸ್ಟಿಂಗ್ ಆಗಿತ್ತು ನಿಮ್ ಟಾಕ್. ಇಟ್ ವಾಸ್ ವೆರಿ ಪವರ್ಫುಲ್ ಪ್ರೆಸೆಂಟೇಷನ್.
Thank you,
I am just coming to whatever Kagli sir has commented. So the finally thermal energy component ಜಾಸ್ತಿ fraction of the energy output ಆಗಿದ್ರೆ, how that is harnessed as the electrical energy for the supply to the grid. ಅದನ್ನ ಸ್ವಲ್ಪ ತಾವು ಹೈಲೈಟ್ ಮಾಡಬಹುದಾಯ್ತು. ಕ್ವಶನ್ ನಂಬರ್ 1 and 2 is how competitive is the cost of nuclear energy compared to other energies, conventional, non-conventional energies and things like that. These are 2 simple questions.
Investment wise, nuclear energy is very costly investment wise, but maintenance wise it is less ಅನ್ನೋದಿದೆ ಒಂದು. ಆಮೇಲೆ ಇದು ಒಂದು ಇದೆಯಲ್ಲ ಗ್ರೀನ್ ಗ್ಯಾಸ್ ದಟ್ ಯು ಕ್ಯಾನ್ ಅವಾಯ್ಡ್. ಅಫ್ಕೋರ್ಸ್ ಇದ್ರ ಇನ್ವೆಸ್ಟ್ಮೆಂಟ್ ಜಾಸ್ತಿ, ಬಟ್ ಇದೇನಂದ್ರೆ ಮೋಸ್ಟ್ ರಿಲೇಬಲ್ ಪವರ್ ಅನ್ನೋದು ಒಂದಾಗಿದೆ. ಇವಾಗ ಹೈಡ್ರೋ ಎಲೆಕ್ಟ್ರಿಕ್ ಪವರ್ ಇಟ್ ಇಸ್ ನಾಟ್ ರಿಲೇಬಲ್. ಟ್ರೈನ್ ಬಂದ್ರೆ ಉಂಟು, ಇಲ್ಲ. ಸೊ ಈ ಕೋಲ್ದು ಪ್ರಾಬ್ಲಮ್ ಏನಂತಂದ್ರೆ ನಿಮಗೆ ಗ್ರೀನ್ ಗ್ಯಾಸ್ ಪ್ರಾಬ್ಲಮ್. ಗೋಲ್ ಇಸ್ ನಾಟ್ ರಿಲೇಬಲ್, ಇಟ್ ಇಸ್ ಮೋಸ್ಟ್ ರಿಲೇಬಲ್. ನಿಮಗೆ ಅದನ್ನ ಪ್ರಾಸ್ ಅಂಡ್ ಕಾನ್ಸ್ ಅಂತ ತೋರಿಸಿದ್ದೆ.
ಸೋಲಾರ್ ಎನರ್ಜಿ ಇಸ್ ಎ ಬಿಗ್ ಆಲ್ಟರ್ನೇಟಿವ್ ಅಲ್ವಾ?
ಟೆಕ್ನಾಲಜಿ ಆ ಟೆಕ್ನಾಲಜಿ ನಾವಿನ್ನೂ ಡೆವಲಪ್ ಮಾಡಿಕೊಂಡಿಲ್ಲ. ನಾವು
ಎಮಿಷನ್ ಬಹಳ ಬರ್ತಲ್ಲ, ವೆರಿ ಲಾಟ್ ಆಫ್ ಎಮಿಷನ್, ಡ್ಯಾಮೇಜ್, ಎನ್ವೈರನ್ಮೆಂಟಲ್ ಪ್ರಾಬ್ಲಮ್, ಹೆಜಾರ್ಡ್ ಪ್ರಾಬ್ಲಮ್. ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಕ್ವೆಶ್ಚನ್ ಮಾಡೋಣ.
ಹೇಳಿ ಸರ್.
ನೆಕ್ಸ್ಟ್ ಕ್ವೆಶ್ಚನ್ ಹೋಗೋಣ.
ಹೇಳಿ ಸರ್.
ನೆಕ್ಸ್ಟ್
ಯಾರು?
ಓಕೆ.
ಯಾಕೆ ಓಕೆ
ಬ್ರೀಫ್ ಆಗಿ ಆನ್ಸರ್ ಮಾಡಿ, ಲೆಕ್ಚರ್ ಕೊಡೋ ಬ್ರೀಫ್ ಆಗಿ ಪಾಯಿಂಟ್. ಓಕೆ
ಓಕೆ
ಮತ್ತೆ ಶಿವಲಿಂಗ ಸ್ವಾಮಿ
ಕೇಳ್ತಾ ಇಲ್ಲ ತಳಿದು
ಹೇಳ್ತಾ ಇದ್ದಾರೆ ಅನ್ಸುತ್ತೆ.
ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡಿದ್ದೀರಾ? ಓಕೆ, ಲಾಸ್ಟ್ ಕೇಳ್ಬೋದು ಇವಾಗ.
ಅದು ಆಕ್ಚುಲಿ ನಂದೇನು ಪ್ರಶ್ನೆ ಇಲ್ಲ, ಅವರು ಇದು KSM ಕೇಳಿದ ಪ್ರಶ್ನೆಗೆ ಆನ್ಸರ್ ಅಷ್ಟೇ. ಆಕ್ಚುಲಿ ಯಾವುದು ಮೇಜರ್ ಎನರ್ಜಿ ಯಾವ್ದ್ರಿಂದ ಬರುತ್ತೆ ಅಂತ ಹೇಳ್ತಾ ಇದ್ರು. ಅದು ಮ್ಯಾಕ್ಸಿಮಮ್ ಎನರ್ಜಿ ಫಿಷನ್ ಫ್ರಾಗ್ಮೆಂಟ್ಸ್ ತಗೊಂಡೋಗುತ್ತೆ. ಈ ಬೇರಿಯಂ ಕ್ರಿಪ್ಟಾನ್ ಅನ್ನೋದು ಒಂದು ಕೇಸ್ ಅಷ್ಟೇ, ಮೋರ್ ದನ್ 137 ಚಾನ್ಸ್ ಇರುತ್ತೆ. ಅದರಲ್ಲಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆಲ್ಮೋಸ್ಟ್ 167 MeV ಅಷ್ಟು ಫಿಷನ್ ಫ್ರಾಗ್ಮೆಂಟ್ಸ್ ಇಂದ ಬರುತ್ತೆ. ಅದು ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಆಫ್ ದಿ ಫಿಷನ್ ಫ್ರಾಗ್ಮೆಂಟ್ಸ್. ಆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಪೆಲೆಟ್ ನ ಕಂಟೈನರ್ ಇರುತ್ತಲ್ಲ, ಕಂಟೈನರ್ ಇಂದ ಹಾರ್ನೆಸ್ ಮಾಡ್ತೀವಿ. ಕಂಟೈನರ್ ಅಲ್ಲಿ ಅದು ಥರ್ಮಲ್ ಎನರ್ಜಿ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗುತ್ತೆ. ಅದನ್ನ ನಾವು ಸ್ಟೀಮ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡೋದು. ಸೊ ಅದನ್ನ ಹೇಳ್ಬೇಕಾಗಿದೆ ಅಷ್ಟೇ. 200 MeV ನಲ್ಲಿ 167 MeV ಅಷ್ಟು ಫಿಷನ್ ಫ್ರಾಗ್ಮೆಂಟ್ಸ್ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಇರುತ್ತೆ.
I agree with you.
ಆಯ್ತು ಬಿಡಿ, ನೆಕ್ಸ್ಟ್ ಕ್ವೆಶ್ಚನ್. ನೆಕ್ಸ್ಟ್ ಯಾರ ಇದ್ದಾರಾ? ಪ್ಲೀಸ್, ಎನಿಬಡಿ ವಾಂಟ್ಸ್ ಆಸ್ಕ್ ಕ್ವೆಶ್ಚನ್? ಯಾರು ಕೇಳ್ಬೋದು. ಈಗ ಇನ್ನೊಂದು, ವಾಟರ್ ಬಿಕಮ್ಸ್ ಕಂಟ್ಯಾಮಿನೇಟೆಡ್ ಅಂತ ಹೇಳ್ತೀವಲ್ಲ, ರೇಡಿಯೋ ಆಕ್ಟಿವ್ ಕಂಟ್ಯಾಮಿನೇಟೆಡ್ ಅಂತ ಏನದು ಎಕ್ಸಾಕ್ಟ್ಲಿ ವಾಟ್ ಇಟ್ ಈಸ್ ಅಂತ ಹೇಳ್ತೀರಾ? ವಾಟರ್ ರೇಡಿಯೋ ಆಕ್ಟಿವ್ ಹೇಗಾಗುತ್ತೆ
ಸರ್? ಇವಾಗ ರಿಯಾಕ್ಟರ್ ಅಲ್ಲಿ ಇವಾಗ ವಾಟರ್ ಗೆಟ್ಸ್ ಇನ್ ಟು ದಿ ರಿಯಾಕ್ಟರ್. ಸೊ ಅದು ಇಟ್ ಕ್ಯಾರೀಸ್ ದ ಹೀಟ್, ಅಲಾಂಗ್ ವಿತ್ ಹೀಟ್ ಆಲ್ಸೋ ಕ್ಯಾರೀಸ್ ದಿಸ್ ರೇಡಿಯೇಷನ್.
ಹೇಗೆ ಅದು? ಕ್ಯಾನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್.
ಅದು ಇವಾಗ ಇಟ್ ಗೆಟ್ಸ್ ಮಿಕ್ಸ್ ಅಪ್ ವಿತ್ ವಾಟರ್, ರೇಡಿಯೇಷನ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತಲ್ಲ ಸರ್. ಫಿಷನ್ ನಲ್ಲಿ ಆಸ್ ಶಿವಲಿಂಗ ಸ್ವಾಮಿ ಸೆಡ್.
ಇಲ್ಲ ಸರ್, ಅದು ಕಂಟಾಮಿನೇಷನ್ ಆಗಲ್ಲ. ಕಂಟಾಮಿನೇಷನ್
ನಾನು ಹೇಳಿದ್ದೇನು ಗೊತ್ತಾ, ಬಾಯ್ಲಿಂಗ್ ವಾಟರ್ ಪ್ರಾಬ್ಲಮ್ ಬರುತ್ತೆ ಅಂತಾನೆ ಪ್ರೈಮರಿ ಸೆಕೆಂಡರಿ ಲೂಪ್ಸ್ ಮಾಡಿ ಅದನ್ನ ಸಪರೇಟ್ ಮಾಡಿದ್ದಾರೆ. ನೀವು ರಿಯಾಕ್ಟರ್ ಅಲ್ಲಿ ಎಂಟರ್ ಆಗೋ ವಾಟರ್ ರೇಡಿಯೇಷನ್ ಮಿಕ್ಸ್ ಅಪ್ ಆಗುತ್ತೆ. ಬಟ್ ಅದು ಹೊರಗಡೆ ಬರದಿರೋ ರೀತಿ ಅದು ಪ್ರಿಕಾಷನ್ಸ್ ನಾವು ತಗೋಬೇಕಾಗುತ್ತೆ.
ರೇಡಿಯೇಷನ್ ಹೇಗೆ ಮಿಕ್ಸ್ ಅಪ್ ಆಗುತ್ತೆ ಅಂತ ಇದು ಫಿಸಿಕಲ್ ಕಾಂಟೆಕ್ಸ್ಟ್ ಅಲ್ಲಿ ರೇಡಿಯೇಷನ್ ಹೇಗೆ ಮಿಕ್ಸ್ ಅಪ್ ಆಗುತ್ತೆ ವಾಟರ್ ಜೊತೆಗೆ ಅಂತ?
ಅಲ್ಲ ಸರ್, ಇವಾಗ ರೇಡಿಯೇಷನ್ ವಾಟರ್ ಮಿಕ್ಸ್ ಅಪ್ ಆಗ್ಲೇಬೇಕಲ್ವಾ?
ಹೇಗೆ? ವಾಟ್ ಇಸ್ ಎಕ್ಸ್ಪ್ಲನೇಷನ್?
ಅಲ್ಲ, ಒಂದು ಲಿಕ್ವಿಡ್ ರೇಡಿಯೇಷನ್ ಸರ್ ಕಂಟ್ಯಾಮಿನೇಟೆಡ್ ಎಲ್ಲ ಕಡೆ ಅಟ್ಮಾಸ್ಫಿಯರ್ ಅಲ್ಲಿ ಇದರಲ್ಲಿ ರೇಡಿಯೇಷನ್ ಎಲ್ಲ ಇರುತ್ತೆ.
ರೇಡಿಯೇಷನ್ ಓಕೆ ನೋಡಿ, ರೇಡಿಯೇಷನ್ ಏನ್ ಮಾಡ್ಬೋದು, ಅದು ಅಯೋನೈಸ್ ಮಾಡ್ಬಿಡುತ್ತೆ ಅಂತ ಹೇಳಿ, ವಾಟರ್ ಅಯೋನೈಸ್ ಮಾಡ್ಬಿಡುತ್ತೆ. ಆಮೇಲೆ ಮತ್ತೆ ಡಿಎಕ್ಸೈಟ್ ಆಗುತ್ತೆ, ಎನರ್ಜಿ ಬರುತ್ತೆ. ಗ್ಯಾಮಾ ಇದು ಹಾರ್ಮ್ಫುಲ್ ರೇಡಿಯೇಷನ್ ಹೆಂಗ್ ಬರುತ್ತೆ ಅಂತ ವಾಟರ್ ಅಂತ. ಓಕೆ,
ವಾಟರ್ ಬರ್ತಾ ಇಲ್ಲ. ವಾಟರ್ ರಿಯಾಕ್ಟರ್ ಇಂದ ಹಾರ್ಮ್ಫುಲ್ ರೇಡಿಯೇಷನ್ ಇದೆ. ಅದು ಇನ್ಫ್ಯಾಕ್ಟ್ ರಿಯಾಕ್ಟ್ಸ್ ವಿತ್ ವಾಟರ್. ಆಸ್ ಯು ಸೆಡ್, ಈಗ ಅಯನೈಸೇಷನ್ ಅದೇನು ಪ್ರಾಬ್ಲಮ್ ಬಂದು ಯು ಮೇ ನಾಟ್ ಗೆಟ್ ಪ್ಯೂರ್ ವಾಟರ್.
ಮೇಬಿ ಇಟ್ ಬಿಕಮ್ಸ್ ಇಟ್ ಸ್ಟಾರ್ಟ್ಸ್ ಎಮಿಟಿಂಗ್ ಅಲ್ಟ್ರಾವೈಲೆಟ್ ರೇಡಿಯೇಷನ್ ಅಂತ ಕಾಣುತ್ತೆ. ಹೈಲಿ ಎಕ್ಸೈಟ್ ವಾಟರ್ ಮಾಲಿಕ್ಯೂಲ್ಸ್. ಅವತ್ತು ಡಿ ಎಕ್ಸೈಟ್ ಆದಾಗ ಯು ಗೆಟ್ ಯುವಿ ರೇಡಿಯೇಷನ್.
ಅಯನೈಸಿಂಗ್ ಫಾರ್ ವಾಟರ್ ಮೇ ಹ್ಯಾಪನ್, ಅದಾಗುತ್ತೆ. ಅದೆಲ್ಲ ಇದೆ, ಸೈಡ್ ಎಫೆಕ್ಟ್ಸ್ ಸುಮಾರು ಇದೆ. ಅದು ಐ ಆಮ್ ನಾಟ್ ಡಿಸ್ಕಸಿಂಗ್ ಹಿಯರ್.
ಓಕೆ, ಎನಿ ಅದರ್ ಕ್ವೆಶ್ಚನ್? Any other questions? ನಾಗರಾಜ್ ಅವರು ಏನೋ ಕೇಳೋದು ಕೇಳಬಹುದು.
ಇಲ್ಲ ಸರ್, ನಾನೇನು ಎಲ್ಲ ಕೇಳಿದ್ದಾರೆ, ಹಾಗಾಗಿ ನಾನು ಪ್ರಶ್ನೆ ಕೇಳುವಂತದ್ದು ಏನಿಲ್ಲ. ಇನ್ನು ಪ್ರೊಫೆಸರ್ ರುದ್ರಸ್ವಾಮಿ ಅವರು ಸಾಕಷ್ಟು ವಿವರವಾಗಿ ಎಲ್ಲ ವಿವರಣೆಗಳನ್ನು ಕೊಟ್ಟಿದ್ದಾರೆ. ಹಾಗೆ ನಮ್ಮಲ್ಲಿ ಅಂದ್ರೆ ಭಾರತ ದೇಶದಲ್ಲಿ ಎಷ್ಟು ನ್ಯೂಕ್ಲಿಯರ್ ರಿಯಾಕ್ಟರ್ಸ್ ವರ್ಕ್ ಮಾಡ್ತಾ ಇದೆ, ಮತ್ತೆ ಹೊರ ದೇಶಗಳಲ್ಲಿ ಎಷ್ಟು ರಿಯಾಕ್ಟರ್ಗಳು ವರ್ಕ್ ಮಾಡ್ತಾ ಇದೆ, ಹಾಗೇನೆ ನಮ್ಮ ಎನರ್ಜಿ ಎಷ್ಟು ಟೋಟಲ್ ಎನರ್ಜಿ ಇದರಿಂದ ಬರ್ತಾ ಇದೆ, ಇದೆಲ್ಲವನ್ನು ಸವಿಸ್ತಾರವಾಗಿ ನೀವು ಕೊಟ್ಟಿದ್ದೀರಾ. ಆಮೇಲೆ ಎಲ್ಲರೂ ಹೇಳಿದಾಗೆ ಸ್ಲೈಡ್ಸು ತುಂಬಾ ಚೆನ್ನಾಗಿತ್ತು, ನಿಮ್ಮ ಪ್ರೆಸೆಂಟೇಷನ್ ತುಂಬಾ ಚೆನ್ನಾಗಿತ್ತು. ಸೊ ಹಾಗಾಗಿ ನಿಮ್ಗೆ ನಮ್ಮ KP ಅಂದ್ರೆ ನೀವು ಬೇಸಿಕಲಿ ನಮ್ಮ ಲೈಫ್ ಮೆಂಬರು ಹೌದು, ಅದರ ಜೊತೆಗೆ ಈಗ EC ಮೆಂಬರು ಆಗಿದ್ದೀರಾ. ಸೊ ಹಾಗಾಗಿ ಮತ್ತೆ KPA ಕಡೆಯಿಂದ ನಿಮಗೆ ಧನ್ಯವಾದಗಳನ್ನ ಅರ್ಪಿಸ್ತಾ ಇದ್ದೀನಿ ಸರ್. ಧನ್ಯವಾದಗಳು ಸರ್. ಮತ್ತೆ ಈ ಒಂದು ಪ್ಲಾಟ್ಫಾರ್ಮ್ ನ ಕೊಟ್ಟಿರುವಂತ ಡಾಕ್ಟರ್ MK ರಾಘವೇಂದ್ರ ಅವರು ಏನು ಜ್ಞಾನಧಾರ ಇದೆ ಈ ಪ್ಲಾಟ್ಫಾರ್ಮ್ನ ಪ್ಲಾಟ್ಫಾರ್ಮ್ನ ಡಾಕ್ಟರ್ MK ರಾಘವೇಂದ್ರ ಅವರು ನಮಗೆ ಪ್ರತಿ ಭಾನುವಾರನೂ ಕೊಡ್ತಾ ಇದ್ದಾರೆ. ಅವ್ರಿಗೆ ನಮ್ಮ KPA ಕಡೆಯಿಂದ ಧನ್ಯವಾದಗಳನ್ನು ಅರ್ಪಿಸ್ತೀನಿ. ಹಾಗೆ ಇಲ್ಲಿ ಈ ಒಂದು ಭಾಷಣಕ್ಕೆ ಎಲ್ಲರೂ ಬಂದಿರೋರು ಎಲ್ರಿಗೂ, ಜೊತೆಗೆ ಕಾಗ್ಲಿ ಅವರು ಇದನ್ನ ಅರೇಂಜ್ ಮಾಡಿದ್ದಕ್ಕೆ ಅವ್ರಿಗೆ ಮತ್ತೆಲ್ಲರಿಗೂ ನನ್ನ ಧನ್ಯವಾದಗಳನ್ನ KPA ಮುಖಾಂತರ ಧನ್ಯವಾದಗಳನ್ನ ತಲುಪ್ತೀನಿ. ಧನ್ಯವಾದಗಳು ಸರ್. ಮತ್ತೆ ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಮತ್ತೆ
ಓಕೆ, ಕ್ಲೋಸ್ ಮಾಡ್ತಾರೆ ಮೀಟಿಂಗು. ಪ್ರಾಬ್ಲಮ್ ಸ್ಪೀಕು ಮೀಟ್ ಮಾಡೋಣ. ಥ್ಯಾಂಕ್ ಯು. ನಾವು ವಿ ಆರ್ ಕ್ಲೋಸಿಂಗ್.
Thank you.
ಕ್ಲೋಸ್ ಆಗ್ತಾ ಇದೆ.